All right. August 25th, derivation of the kinematics equations. So I'm going to derive 5 equations ultimately, but we only have one thing. The only thing that we have right now is that we know that V average is V average is equal to delta X divided by delta T. That is literally the only formula that we have right now to work with. So the first derivation must come from this formula because it's literally all we know. So I am going to make a quick switch. I am going to write, actually, I'm sorry, I'm not going to make a quick switch. I'm going to make a claim. I'm not going to prove this, but I'm going to make a claim. You remember the Disney World problem where we said we could not get the average velocity by averaging 40 and 60 and getting 50? We had to do it the long way and we got 48. Well, that was because there was a change in acceleration when I turn around to come back the other way, my acceleration is changing at that point from positive because I was headed north to negative because I'm headed south. So acceleration is not constant, and that's what broke that problem. But actually, if you have constant acceleration, then you can just do the average in the way that you would expect. So this is true, and I'm going to go ahead and I'm going to label this to remind you. This is true only if the acceleration is constant. So that's a caveat. And that's why it is important to remember that we are in the constant acceleration model. Because if we were not in the constant acceleration model, then this would not be true and we could not do this step. But since we are in the constant acceleration model, A is constant, and I can do this averaging process. And then both of these are V average, so what am I going to do? I'm going to set them equal to each other. So I'm going to set delta X over delta T equals 1/2 V initial plus V final. And then I'm going to multiply by delta T. So I'm going to have delta X equals 1/2 V initial plus V final delta T. And I'm going to prove why I can do this in a second, but for the moment, I'm just going to stop calling it delta T, and I'm just going to call it T. So I'm going to write it as delta X equals 1/2 V initial plus VF times time. And that is our first kinematics equation. I am not going to label it kinematics equation number 1. You'll see why in a minute. There are 3 kinematics equations that are normally called 1, 2, and 3. So maybe you can call this one kinematics equation 0. Okay. And then just quickly as a sideline, the reason that I can, instead of delta T, I can just use T is delta T equals T2 or T final minus T1 or T initial, right? Those are arbitrary, so I can pick whatever I want. So I am going to pick T initial equals 0 and T final equals T. So that means that delta T equals T final, which is T, minus T initial, which is 0. T minus 0 is T. Boom, I have just proved that delta T is equal to T. So wherever the book uses delta T, I'm just going to use T because it's easier. So that is the first of our kinematics equations. So now I am going to derive a second kinematics equation. I'm sorry, I'm checking. The slides seem out of order. The order in which they do things doesn't make sense. All right, so I'm just going to go my own way and not follow the PowerPoint anymore. I'll fix the PowerPoint later. Let me write a note. All right, so so we use velocity. So coming back over here, we used velocity and we derived an equation. So now what we're going to do is we're going to use the second thing that we know. We only know one other thing. We know velocity, and we know that acceleration equals delta v over delta t. And again, we're going to not call it delta t anymore. We're just going to call it t. So that is our second definition that we know. Those are literally the only two things we've learned in this class so far. V is delta x over delta t, and A is delta v over t. And then I'm going to make the same substitution. Delta v is v final minus v initial. So v final minus v initial over t. And now I'm going to just do a little bit of algebra. So I'm going to multiply by t. I'm going to have AT equals VF minus VI. And then I'm going to bring VI over. So I have AT plus VI equals VF. And then I'm just going to write it in the usual way. This is usually written VF equals VI plus AT. And this is what's usually called kinematics equation number 1. And this is critical. This is so important. It's actually on the formula sheet. But again, as I told you before, the formula sheet sucks because the stuff on it is the stuff that you're going to have memorized from using it so much. This equation is going to come up so often, you're just going to know it by heart. This is equation 2.13, and it is on page 36 of our book. So that is the first kinematics equation. All right. I'm going to go on to another derivation. So now we know a little more, and that's usually the nature of when you're deriving stuff is you start from 1 plus 1 equals 2, but then as you build up more things, you have more tools to derive stuff. So I had the definition of V and I got an equation, and I had the definition of A and I got an equation. Now I have two equations to derive stuff. So I'm going to actually write them both back at the top of this page. So I have VF equals VI plus AT. I just derived that. And if I go back to the first page, I have delta X equals 1/2 V initial plus V final times time. And now this is cool because I have two distinct equations that I can use. So what I'm going to do is I'm going to take VF right here, and I'm going to plug it. Sorry, I'm going to plug it in there for VF. So I'm going to have delta X equals 1/2. VI is just VI, leave it alone. And then VF is this thing. So VF is VI plus AT. And now I'm just going to do some algebra. I'm going to combine, right? So VI plus VI is 2VI. And now I'm going to distribute the 1/2. 1/2 times 2VI is just VI. 1/2 times AT is 1/2 AT. And now I'm going to distribute the T from the other side. Obviously, I could have done these two multiplications in one step, but I wanted to make it absolutely clear what I was doing. VI T plus 1/2 A, and T times T is T squared. And this is kinematics equation number 2. Also on our formula sheet and also critical. And this is equation 2.16 on page 37 of our book. All right. I always get confused because I never remember the algebra for this next one. If I get stuck, you guys will have to help unstick me. But I'm going to try to do a different thing with this equation. So I'm going to go back to the same two equations. VF equals VI plus AT. And what is the other one? Delta X equals 1/2 VI plus VFT. And I already took VF and plugged it in here and got some stuff, so that was fine. So I'm going to try a different substitution. And what I'm going to try is I'm going to solve for T. So I'm going to solve this for T. So AT equals VF minus VI. And now T equals VF minus VI over A. And so now I have T. And I'm going to take T and I'm going to plug it in there. So I have delta X equals 1/2 VI plus VF. And then T is going to switch. So T is going to become VF minus VI over A. 2 is dividing, so I'm going to bring it over multiplying. So I'm going to have 2 delta X. And A is also dividing, so I'm also going to bring that over multiplying. So actually, I'm going to have 2A delta X, right? Delta X, 2, and A. And that leaves me with 1/2. VI plus VF is the same thing as VF plus VI, so I'm going to switch it, and you'll see why in a second. And then over here, I have VF minus VI. And I'm sorry, did anybody see the mistake that I made? What mistake did I make? What did I write that I should not have written?
The 1/2.
Yes, the 1/2 was already taken care of. So the 1/2 should not be there because I already moved it to the other side. Okay, so half is gone. So this is correct now. Okay, now why did I go through the trouble of switching the VI and the VF? Does this look familiar?
It's quadratic, or
It's a quadratic, but
A
specifically
plus B.
Difference of squares.
Right, that's correct. It's difference of squares, so this is just V final squared minus V initial squared. I'm going to bring VI over. And then I'm going to make a couple of switches. I'm going to switch the order around, so it's going to be V final squared equals V initial squared plus 2A. And I'm not a fan of delta X, so I like D. So I'm just going to make the substitution that delta X is equal to D by definition, just so that I can use D. All right. And this is kinematics equation number 3. And it is, this is equation 2.17, still on page 37. All right. So this is what's usually derived. This is the standard derivations. When I did physics 3 times when I was first starting out in physics. I did physics honors as a junior. I did AP physics as a senior. And then I didn't get credit. I didn't get a 5. My school only gave AP credit for 5s, and I got a 4. So when I went to college, I had to take 2048, physics 2048 again. So I did it 3 times. And all 3 times, these are the only 3 kinematics equations that were derived. And I never thought anything about it. And then a couple of years ago, after I was already teaching at Everglades, the first year I taught at Everglades, this is exactly how I did it. This is all I did. But then after I'd been teaching at Everglades for a little while, I read some article for physics teachers, and I thought it was fascinating. And I'm going to summarize that article for you. So I'm going to make a new page. I'm going to make a new page, and I'm going to summarize what this article pointed out to me that I thought was brilliant. I'm going to write down the 4 kinematics equations we have written down so far. That was one. This was another one. And then this was a third one. And then this was the last one. I guess I should be consistent. I'm sorry. So if I changed it to D in that last one, I should change it to D everywhere. So just for consistency. And if you look, so then you can make a grid of all of these equations. And there's 5 variables. There's V initial, V final, A, T, and D. This first equation has V initial in it. It has V final in it. It has A in it. It has T in it. but it does not have D. This next equation, it has D, it has V initial. I'm sorry, this is the wrong, this is, obviously I shouldn't have colors all over the place. I should use consistent colors. I should use this. So this one has D, and it has V initial, and it has V final, and it has time, but it does not have acceleration. The third one has D, has acceleration, has V initial, and has time, but does not have V final. And then this fourth one has V initial, V final, A, and D, but it has no time. Okay? So you'll notice there's a pattern. There's one that doesn't have D in it. There's one that doesn't have A in it. There's one that doesn't have VF in it. And there's one that doesn't have T in it. All of them have V initial, which presents a problem. If I give you a kinematics problem that does not have V initial, that problem becomes a two-step problem. Step one, figure out V initial. Step two, answer whatever it is that I'm asking you about the kinematics problem. It would be awesome if there were an equation. So I'm going to extend my table. And I'm just going to speculate. So I am going to wish that there were an equation that had VF, A, T, and D, but did not have V initial. And I would like there to be such an equation. Yes, go ahead.
Can we use equation 3 and instead of using V initial, use V final?
Almost. There's a sign error also. There's a sign difference.
Because it's going to be minus 1/2.
Correct. And we're going to derive that. And then that will be our fifth equation. That fifth equation is not in our book. It is not in most books, but it is an incredibly useful equation. So that's what I'm going to do. The last thing I'm going to do is I'm going to add a page to this, and we are going to look at this derivation where I got delta x, and we're going to just change it up. So I'm going to start from the same two equations, but I'm going to change up what I did a little bit, and we're going to get a new equation. So we started from VF equals V initial plus AT, and then the other one was delta x equals 1/2 V initial plus V final T. But the change is I took VF and I plugged it in here. So that left me with just VI in my equation. But what if I rearrange this one? What if I make this one VI equals VF minus AT? And that's where that minus sign comes from that I was talking about. And then I'm going to take this and I'm going to plug it in here to get rid of V initial. So I'm going to get rid of V initial and only have VF. And that's going to give me that fifth equation that I've been hunting for. So delta x equals 1/2. V initial is V final minus AT. And then VF is just VF, leave it alone. And then I'm going to do the same steps I did before. So I'm going to go a little faster because these are the same steps I did before. 1/2. VF plus VF is 2VF. Minus AT is still there. Distribute the 1/2. So 1/2 times 2 is just VF minus 1/2 AT squared. Sorry, not AT squared yet, just AT. And there's still a T out here. Now distribute the T. I was jumping ahead. And I get VFT minus 1/2 AT squared. And then last step, D equals VFT minus 1/2 AT squared. And this is the elusive fifth kinematic equation. And I can't give you an equation reference because this isn't in our book. But now I can go back over here, and there we go. D equals V final T minus 1/2 AT squared. And I can get rid of the question mark because, yes, this equation does exist, and I just derived it. So these are the 5 kinematics equation. that we will be using to solve all of the kinematics problems. So basically next class, I'm sorry, you guys didn't stop me. We are so over time. I apologize, guys. Sorry, it's 11:42. It is lunch. Go enjoy your lunch. I'm not going to say another word. I'm going to stop recording. We'll pick it up right here. I can't believe nobody stopped me.
We enjoy learning.
Mr.
All
Luis,
right,
you're
this-
so excited for the elusive equation.